Okay, welcome back for the second session. So Professor Ghate from TIFR is going to talk us about deformations of reducible Galois representation with large Selmer theorem.
Thank you, Eric, and you can hear me. Thank you to the organizers, especially Somnath and Ashay and Haruzo who are here for this chance to speak here. This is a joint work with Anvesh, who's sitting over here. We're wearing the same color shirt, that's a kurta, so you can recognize him. I actually met him here for the first time a year ago, a year and a half ago maybe. So ICTS has some advantages. Broke the ice, and we started working on this for a year, and we posted this paper on the archive about 3 or 4 weeks ago. So you can check it out. Let me start with the theorem. So this will be mostly an algebraic talk, no connections to periodical functions, but it's about Selmer groups. So fix a prime, e at least 5, fix an integer n is not the level, it's some Selmer group will be bigger than n. Then the claim is that there's a p-adic Galois representation, a p-adic x0 Galois representation, integral version, T is the lattice, B is T tensor QP, the usual notation, such that the dimension GL2. Yeah, no, I'm not VTech again. So dimension of FP of the Selmer group this Bloch-Kato Selmer group, which I think has shown up many times, but I think there are some students around, so maybe one should define it. So the P torsion in the Bloch-Kato Selmer group for A, so A is usual notation for V1T. The dimension of FP is greater than equal to n. You can make it as large as you want by picking row suitably. A, of course, depends on row. So the idea here goes back to a small and beautiful paper of Matsuno. Who proves something similar, but for elliptic curves. So I won't say much more than just that. So two elliptic curves E over E and E prime over Q, related by a cyclic p isogeny. It's cyclic anyway. So his idea was to somehow look at Selmer groups over the cyclotomic ZP extension and show that their ranks were the same, lambda ranks were the same, and then somehow use that to make 1 over Q large and 1 over Q small. So it's kind of based on this, but elliptic curves don't appear explicitly here. Okay.
Yeah. What do we know about the ramification of rho?
Yeah, so that's a very key point, and I'll explain that in the proof. You have to keep adding primes of ramification to a particular row bar that we start with. And the choice of those primes is quite explicit. So this whole proof is based on a method of Anvesh's advisor, Ravi Ramakrishna, who did something very remarkable. He started with a reducible multi-representation and lifted it to an irreducible characteristic zero representation before, without any Serre conjecture or anything like that. But at the expense of adding some primes or ramification. So it's a very explicit method, and that'll show up in the proof. Yes, this was for small primes, and I think that's more or less required if you're working with elliptic curves over Q. Okay, so I'm going to move slowly. So Selmer groups. I tried to scan some of the videos last week, but I think Professor Nakamura defined some Bloch-Kato Selmer groups. Other people did also, but I never saw exactly the one with divisible coefficient. But of course, it's all implicitly there. So let me just define this. So before I do that, here's the cyclotomic VP extension, U infinity. And I will write gamma for ZP, usual notation. Q0 is just Q. I'll fix a row from the Galois group of Q to GL of a lattice, two-dimensional module over ZP, sitting in GLV. And I'm going to assume that the Tate dual of V is isomorphic to V, self-dual. So Hom V QP1 is isomorphic to V. And A is V mod T, and with this notation, the Bloch-Kato Selmer group of A over Qn is the kernel H1 Qn with A coefficients to product of all primes. And wondering how much detail to go into here, but this H1 finite has come up many times. I think all the experts know what it is. Just for the students, there's a little maybe confusion because you're putting A coefficients. So it's the image of H1 there's a natural map from V to A. A is a quotient of V. So this has appeared many times. Take the image of this in here. That's the definition of this. And this is fairly standard, perhaps to many experts here. Let's write a few notations. So for V not dividing P, it's just the unramified classes. It's the H1 classes, which on inertia are trivial. So kernel of the map from H1 QNV to H1 INV, V coefficients. And for V dividing P, it's this famous occurrence of B Chris, which appears. The kernel of this map. V is not, V divides P. Okay, so that's the Bloch-Kato Selmer group, and over Qn, and you can define the Bloch-Kato Selmer group over Q infinity to be the direct limit of these finite level Bloch-Kato Selmer groups. So it's an action of gamma, which is the Galois group of Q infinity over Q. Okay, so this is the object of interest, but for the proofs, there's another Selmer group that plays a role, appears. So that's the Greenberg-Selmer group. Be a bit more terse here. It's also a direct limit. The Selmer group of Greenberg-Selmer group of A over Q infinity is the direct limit of these finite level Selmer groups, where I break the rule. This is not supposed to be a recorded talk, so you can go beyond the border to the line of actual control. So I'm giving it for the first time. I requested them not to record it. So if you can see here, that'd be good. I like to write bigger and use more space. Okay, so yeah, the Selmer group, Greenberg-Selmer group of A over Qn is the kernel very similar. But let me define it. H1 QNV A to over all V H1 QNV A. Local conditions are a bit different. You are modding out by something. So let me try and do both at the same time. So H1 NRA, which is just the unramified classes, but this is easier than taking the unramified classes for V and projecting to A. You just directly take the unramified classes with A coefficients. So this is if V does not divide P. And if V divides P, you put the ordinary condition here, which involves a bit of notation. So let me not get into it, but I think everybody knows what that is. So here's a filtration, A plus A minus, and you want the kernel of the restriction map from that group to H1 INV A minus. This is the Greenberg-Selmer group. And the important thing for us is that these two Selmer groups are related because these local conditions are related. It turns out that these local conditions are sitting in those local conditions with finite index. So you get an exact sequence. Yes, yes. So here there's an ordinary condition. So the local conditions for the Bloch-Kato Selmer group are sitting inside. The H1Fs here are sitting inside the local conditions for the Greenberg case. And the first map, kernel is sitting in this kernel. And this is just from group cohomology. Okay, so we have that. We also need a local version of this. So similarly, and this is slightly important, so there's a map HL, one for every prime L, from H1. Let me switch to, so I'm writing V when N is arbitrary, but when the base field is Q, let me write L instead for the generic prime. So L is P or L is not P. Ramified or depending on if L is not P or L is equal to P. And then back to V because N is arbitrary here. So HL is this whole map. This map is just induced by restriction, and this map is coming from the fact that H1F lies in here. So let HL be this map, and maybe I'll go even a little further. We will define delta L of A, where B prime A, to be the kernel of this map. The kernel of HLA, P torsion of it. And it's a fact, right, a little bigger here, that this is either, it's bounded by 2 or 6. If L is not equal to P, L is equal to P. Some notation that one needs, local information that one needs in the proof. Oh, they're following me around. Great.
Exact in the middle, neither injective nor surjective.
Yeah, so this first map is injective. The second map I'll have to think about. But I think this composition of this whole map is actually injective. We proved this in our paper. So certainly that only implies this map is injective. This map I'm not completely sure about. No, this is just an inclusion and this is just a projection. I mean, not projection, but just another inclusion. I mean, it's just a map, yeah, by restricting classes. I don't know if the kernel of this is the image of this. That I don't know. Yeah. But the whole map turns out to be injective, but that's a little exercise, I think. Yeah, there's some Selmer group experts here like Sujata and Somnath. Yes, yes. It comes up in the proof. Comes up in the proof. I was trying to tell you that by Matsuno's result, you work over lambda. That's one of the big insights of Hida. Working over lambda, many things are easy. And then you descend back to Q. Yes, everything's going to be ordinary at P. Yes, yes. In fact, the reason it's modular is because of Skinner-Wiles, because it's ordinary at P. You can actually say it's modular. Okay, so that was the definition of the Selmer groups and some relation between the Bloch-Kato and Greenberg-Selmer groups. Okay, so now I want to do some Iwasawa theory. So, usual notation, lambda is ZP power series T, which is secretly ZP power series gamma. Or rather the other way around, maybe. M is finitely generated lambda module, torsion. We let GM, Nakayama lemma kind of thing, you take dimension over FP over M mod the maximal ideal of lambda, which explicitly is just this. And there's also a dual way to express this dimension. You can take the Pontryagin dual of M, take the gamma invariance, and take the P torsion. The operations are dual to taking going modulo T and going modulo P. It's also this dimension where M dual is the Pontryagin dual. So the first proposition in the paper is to relate. Oh, sorry, I need one more piece of notation. So I want to shorten, instead of speaking of G of the Selmer group, let me just call it G of A. So G of A is the G of the Selmer group. So this is a lambda module. And take its Pontryagin dual to make it a compact type thing. There's divisible coefficients. Take its Pontryagin dual, and G of this is defined to be G of A. So here is a first proposition in the paper. It says, by looking at various exact sequences and splicing, separating two exact sequences apart, etc., one can prove that G of A, this number, is greater than or equal to the following sum of deltas. The ramification of rho is the set of primes that ramify in rho. It's a finite set of primes. I may forget to include P here, but P is usually ramified anyway. I write it here explicitly, but P is in that set. So it's the sum of delta LAs. That is the content of the proposition. At least that big. So this is useful because you're trying to bound some Selmer group lambda-adically, and if you can make these are supposed to be the analogs of Tamagawa numbers for elliptic curves. Delta LA is defined right at the end. Sorry, it's the, yeah. Is it the dimension or the size? Dimension? Sorry, I forgot the word dimension. Defined right at the end there. Yeah, I think the Tamagawa numbers are the size and the deltas are the dimensions. So the result says that if the Tamagawa numbers are large, then the lambda-adic rank of the Selmer group over Q infinity is large. Supposedly, yes. That's my understanding, yes. Okay, so say now, let's a little bit of notation. I want to apply this. So say now that your original Galois representation or some Galois representation acting on T, on a lattice T, is of the form, it's reducible. This may look a bit strange, but I'm going to write it as pi psi bar star 0 psi bar. Okay, so suppose that you can choose a basis such that mod P, this representation is just semi-simple. B is just a sum of characters. Form phi psi bar. The 0 here is important, so it's reducible. And usual notation, let V be T tensor QP, A be V mod T. Then you can pick another lattice T prime such that the mod P reduction is lower triangular. Ribbit kind of statement. And another basis, E1 over P, E2, small computation. And so V is still, V doesn't change, of course. You tensor with QP, but A prime changes because it's sensitive to the denominator. So we'll soon be in such a setup. Sorry? Yes. Don't think so. I think P is okay. P is okay, yeah. Okay, that star may not be, maybe 0 is what you're saying. Okay, so where were we? Yeah, so suppose this is the setup now. I want to actually apply this fact. So note, A and A prime are related by a cyclic T isogeny because T is sitting in T prime. Index P, so V mod T maps to V mod T prime surjectively. Kernel has size P. Take the dual isogeny. Get a map from A prime to A. Apply Selmer groups. Maybe I'll skip a step. Apply Selmer groups and take dual. Von Dragon dual. You get a map from Selmer. Okay, so one has this situation. So these are two lambda modules, and you have a natural map between them. So here's one of the results of Matsuno, which is probably well known, but the proof is given there. The result of Matsuno is the following proposition, that if X is a finitely generated torsion lambda module, by the way, by some result of Kato, all these things are torsion lambda modules. And Y is a submodule such that the quotient is an exponent P, then the number of generators of X, minimum number of generators of X is greater than G of Y over 2. Okay, so what do we want to do? We already have this bound. And so trivial fact, this is greater than or equal to N if there exists L1, L2, Ln primes, ramification locus, such that delta Li of A is greater than 0. You can find N primes with these deltas positive, then obviously this number is bigger than N. You go back over here, you call this X, call this Y. It turns out that this map is injective of exponent P. So it fits into Matsuno's setting, and think of Y as a submodule. And it tells you that the Selmer rank, the G of A prime is bigger than G, so which is so we see that the Selmer rank, the number of generators of A prime is at least n by 2 by this result of Matsuno. Okay, and we make this a bit more precise. I'm going to call this a splicing argument, and breaking up some snake lemma type exact sequences is a map between these exact sequences, breaking up into two parts, not completely exact, doing a bit of algebra, implies that there's a following map. Exactly, this is really exact now. E torsion. doing this for A prime. So the Bloch-Kato-Selmer group of A prime over Q maps to the Greenberg-Selmer group of A prime over Q infinity. That's the composition of the two maps that I raised on this board. Turns out to be injective, as I was saying. And then finally, you have a map to these local Tamagawa number type things. Okay, so this is maybe not so surprising just because of some of the definitions I wrote down over here. So you have such a short exact sequence, and this implies that there's a gamma invariance here. Thank you. HL of A, yes. Did I write A there also? Yes. Everything depends on A prime actually in this case. Thank you. HL of A prime. So since this is not necessarily surjective, if it's surjective, then you know that the dimension of this is the sum of the dimensions, but you don't know it's surjective, but at least you get the following inequality. That the dimension over FP, we want to go to the Selmer P rank. So the dimension of this is less than or equal to the sum of these dimensions. So just moving this term to the other side, you get this. And we already said that if you can find such primes, which is the tricky part of the argument, well, so this is bigger than n by 2 minus this sum over delta L A primes. So what's the game? The game that one is trying to play here is that you want to try and add primes of ramification to rho such that this number keeps getting larger and larger. So this is great, but there's a price to pay. These Tamagawa numbers might also be getting larger and then nothing might be happening. You might not be going to infinity. So you have to sort of control these and show that there may be zero, for instance, or at least whatever primes you add so that you can lift to characteristic zero. Most of the time, for all but finally many primes, these delta L Tamagawa numbers are zero. Then you'll win because this will go to infinity, and this is for any n, so you can make the Selmer rank as large as you want. Okay, so now I come to the actual construction of rho. As I mentioned, this goes back to a paper of Hamlin Ramakrishna, who proved that you could lift reducible rho bars to characteristic zero without any modularity assumptions of any kind. In fact, they conclude at the end that the lift was modular by Skinner-Wiles. That's a good question. So I think we just mostly for simplicity assume that the Harshay weights are 0 and 1. It's just an abelian variety, GL2 type. So we had to modify Hamlin Ramakrishna because their Harshay weights were a bit large, but they assume they're large to kill various things. But we had to redo some of their lemmas, which in our case. But I think that's not so serious. You could probably do it for any weight. Oh. Which two Selmer groups?
Bloch-Kato Selmer.
Okay. Yeah. Sorry, what are you saying? Answer your question. I don't wait for. Okay, so some deformation theory. So here is an auxiliary theorem, which is a bit more technical than the introductory theorem and theorem from the introduction, beginning of the talk. But this theorem is very similar and will imply the main theorem. So maybe I didn't put the reference. This is archive 2504 point something. This is already on the internet. So this is theorem 5.7 from that paper. Anyway, it's the sort of main technical theorem. So it's a redoing of Hamlin-Ramakrishna in our setting to make these Tamagawa, control the Tamagawa numbers as you're lifting. Let p greater than 5 and greater than or equal to 1. And let rho bar be a reducible null representation. GL to FP. Such that this star is non-zero, it's indecomposable. And the second condition is a slightly technical one. Phi is of the form, the mod P cyclotomic character, I won't write that down, times the beta squared, where this is not 1 for beta equals mod P character. Odd unramified at P character. Order P minus 1 or order killed by P minus 1. Then there exists a lift. Now I'll start specifying the set of primes of ramification Gx, GL2T rho, GL2T rho, GLT rho, lifting rho bar. Such that the dimension of the Selmer group, same conclusion, but for A prime this time. So again, to remind you again, this is to answer Eric's question, the determinant is actually cyclotomic character times diagonal lift of beta squared. So it's a weight 2 situation. There's some other facts. And what is this A prime? So V is, you twist V rho by psi, for psi to be beta tilde inverse. E is similarly the twist of T rho by psi. And A is V mod T and A prime is V mod T prime. But more importantly, A prime is V mod T prime. So this A prime shows up here. So there's always two so-called elliptic curves or floating around, or two divisible groups floating around, A and A prime. And this one is the one that's large. As you can see, we're going to start using these inequalities here. Okay, so we want to adapt. So now I tried to define almost everything at till this point. So now I'm going to start sketching the proof. There will be maybe some things which I won't be able to define. This will turn out to be modular, yes. This is also modular. So that part is kind of for free, given the work of Skinner-Wiles, because what we're going to do is we're going to assume that when we lift, there's a p-ordinary condition. So rho will be a p-ordinary lift. It turns out to also be irreducible because of somewhere some clever argument of Hare, Larson, Ramakrishna says that you can lift so that rho 2 is irreducible. The lift to z mod p squared is already irreducible. So then you can lift to characteristic 0, it's irreducible. It'll turn out to be odd because rho bar is odd. It's like that, and you can apply Skinner-Wiles, ordinary at p. To get that, it's modular. That's incidental for free. I mean, that's just, yeah. I mean, it's of extra interest in some sense. I mean, one doesn't really need it. Another question? Okay, so proof. So we adapt the method, which is classical to a certain set of people, like Khare and Larson and Bokla and Ramakrishna, etc., but maybe not so well known in this room, for instance. So I thought I'll try and sketch some of those details. Adapt the method of Hamlin and Ramakrishna. The paper in the American Journal of Math. To our setting. So let's see. Since I'm running out of space, let me squeeze in some things here. So step 1 is just a preliminary step. The steps I'm going to list are, step 2, for example, is lifting to z mod p squared. Step 3 is lifting to z mod p cubed, and so forth. Step 4 will be lifting to z mod p to the 4, and then after that, you can just lift. Okay, so I need to speed up a bit, so some notation. So let sigma be basically the ramification set of the mod p representation. Let's throw p in there explicitly. So there's some deformation conditions, which I'll call CL and NL. For all L in sigma, with these same conditions as in HR. This is to allow local lifting to happen. Sort of their game is that locally you can lift the Galois representation, and then some H-F-H group is trivial, so globally you can also lift the Galois representation. This is the way that they work, and they keep adding primes where locally you can lift the Galois representation. Okay, so where was I? So yeah, this is CL is just rho bar restricted to L, the deformation functor of rho bar restricted to L at some condition. CL and NL is, I wish I had some more space, maybe I'll write it here. It's a sub of H1 GQ add rho bar. Come behind the add 0 rho bar. Okay, so they have a table in which they tell you what conditions to put at the start on rho bar. Okay, some more preparatory sets of primes. So now we enlarge sigma to x naught so that some shahs vanish. This is very useful because we want to globally lift things when it's locally liftable. So this is also part of HR. Pick x naught contained in sigma. These are what they call trivial primes. So these are primes L congruent to 1 mod p, but L not congruent to 1 mod p squared, and rho bar restricted to QL, Galois group of QL, GL, is trivial. So let me not define all that, but there's some special primes L that you enhance this set sigma by. All the enhancing primes, I think, are trivial primes, so some technical point, very useful in the arguments, such that the local SHA-1, not local SHA, sorry, the first stage SHA-1 of M, I wrote M here, yes, for all submodules M sitting in add zero rho bar and add zero rho bar tedule. Okay, so the first step is that you can enhance the set sigma so that the SHA-1 is 0 for all Galois submodules of these two groups, these two modules, the adjoint star. Pick, I'm going to try and give a sketch, but try and give details so that it's not completely superficial. So they have something called type 1, type 2, and type 3 primes. So they impose that at these primes, there's some deformation conditions, you impose them. So these CLs are and Ls are of type 1 for all L belonging to X0 minus sigma. So this is one more thing. And then one more little preparatory step, which is independent of this step. For all n greater than 1, n is the same n that showed up earlier. We want to make this Selmer group number of generators bigger than n by 2 minus something. The Selmer P rank to be bigger than n by 2 minus the Tamagawa numbers. So that n, pick L1, L2, Ln, trivial primes. Yeah, so these types are defined in the paper, in our paper as well. Yes, the level raising primes. Yeah, okay, as in the sense of measure. Yes, it looks like it. Right. Yeah, nice observation. Yes. Measure and ribbit. So one of the lemmas in our paper says that this is good because delta L of A prime is 0, and simultaneously delta L of A is 1. So you're winning both ways. You're making the A Tamagawa numbers large, but just what we wanted over there, right at the beginning of the talk, but we want the A prime Tamagawa numbers to be small because we're subtracting them from something. So we don't want them to be too big. So pick such primes such that I'm going to use some notation, the Selmer groups. You can guess what it is. This Selmer group with local conditions n, so just the kernel from H1 to local H1's modulo NLs. The dimension of this is less than or equal to M, where M is by definition, X1 is now a bigger set of primes. Maybe we should define it first. So this is X0 union L1, L2 up to Ln. Okay, so this is a technical point that you need to pick these trivial primes such that this particular Selmer group is bounded by something which purely depends on rho bar and maybe a few more primes which kill some SHAs. Okay, so that's the preparatory step. Now we can start lifting. So step 2 is easy. So the obstruction to lifting rho bar from gx1, right? Think of rho bar now as a with domain, the Galois group with possible ramification at x1. Sorry, rho bar is still sigma, but to an element xi2 from gx1 to gl2 z mod p squared. We want to lift this from mod p to mod p squared with some primes attached, ramification primes attached. So this lies in SHA2 x1 u1. So u1 is one of these submodules M. It's the upper right corner in the adjoint at 0. But this is dual to, well, this is first of all contained in SHA2 x0 u1. This is dual to SHA1 x1 u1 a dual, which is 0 by step 1. So the obstruction lies in some Tate-Chapman-Fitch group, which vanishes, so you can lift it. So rho bar, let me repeat it, it's not a waste of time. So this part is not so bad. Okay, step 3 is tricky. By the way, at this stage, we don't yet know whether this rho bar is irreducible, but that will be the content of the next step. Remember, the lifts are principal homogeneous space under some H1 as your rho bar. So you can move them around. So you may have both reducible lifts and irreducible lifts. So this is part of the argument of KLR, but it's a bit more subtle than that because they want to actually lift to Z mod P cubed. Okay, so this is also in HR 08, but the idea goes back to KLR, Hare Larson Ramakrishna. So this says that there are two more primes. L belonging to capital Z, that is by definition those two primes. So now they take CL and NL of type 2. Type 2 hadn't shown up yet. So some deformation conditions, but they're of type 2. And this is a 2. And there's also a global cohomology class, H1, GX2, add 0 rho bar, where this X2 is X1 union these two primes. Such that let me go over here. Such that the twist of rho 2, the twist rho 2 of xi2 by z, that's identity plus pz, just backed by this H1 class on xi2. Right, so they twist this particular lift by z, and this particular lift actually lifts to its. So first of all, this is irreducible. This is one of there, and lifts to xi3 from gx2 to gl2 z mod p cubed. Okay, so this was a very important and I think big obstruction in the business, going from GL2 Z mod P squared to GL2 Z mod P cubed. But for us, it's not serious because you're only adding 2 more primes. So that's bounded error when you look at the Tamagawa numbers. Type 2 primes, we don't know anything about the Tamagawa numbers. May not be 0, delta L of A prime. But there are only 2 primes, so that's okay. And finally, step 4 is the last step. This is the sort of general step. It's very clean. You have to do a little bit of racing of the car engine to get your car running, but once the engine is running, drive off smoothly. Step 4, which I'll call plus because you're lifting to Z mod P to the 4, but even higher. So there exists, this is also from HR, M trivial primes, Q1, Q2, up to Qm. Remember, M was that number which was defined down here. It was some H1, which only depended on rho bar. So these primes may be different for different rho bars, but the number is all we care about, and that's bounded by, in terms of rho bar. With CQI and QI of type 1. Did I say something wrong? I think. Oh, yeah, actually, these type 2 primes, we do know that the deltas are 0. We do know the deltas are 0. So, but here we don't know the deltas are 0. This is a problem. Type 1. But it's bounded. There are only M primes which depend on rho bar. So that's okay. Such that and finally we have the set X. Has to appear sooner or later because it's the final step. So H1, Selmer H1 GX, add 0 rho bar is isomorphic to the direct sum of L belonging to X, H1. Oh, yeah, so this happens, but the reason this happens is, yeah. So let me, such that some dual Selmer group, GX add 0 rho bar, some Selmer group and some dual Selmer group both vanish. So there's some trivial primes which kill both the Selmer group and the dual Selmer. This step is called killing Selmer or something like that. Killing dual Selmer maybe. So because of this restriction map here is an isomorphism because the kernel and co-kernel vanish. This is an isomorphism. Okay, the kernel is by definition the Selmer group, and the co-kernel, by potutate, the co-kernel also vanishes. So this is good because now you can choose FLs, some local H1s, for L belonging to X, such that, so identity plus P squared FL times xi phi restricted to L belongs to CL, where CL is this deformation condition of type 1. So you can knock it by these FLs to make sure that it satisfies this deformation condition because this is a transitive action on lifts. And these NLs preserve CL, so it's a well-defined element of this quotient. I didn't say that at the beginning. So you get a tuple here, and by this isomorphism, this comes from an F. which maps to this, which is a global H1. And then finally, you let row 3, same thing, be p squared f times I3, so globally. And this lifts to Xi4. From Gx to GL2 Z1 beta 4. Since again the obstruction is in a SHA-2, but SHA-2x at 0 bar, this is the same argument every time, is 0 because it's sitting in SHA-2x naught, etc. I already did that argument once. So locally liftable implies globally liftable if the Tate-Schafer average group is 0. So up to this step, you're fine, and then you can continue this step, the step you now repeat inductively, and you can finally lift to a row. Let's take a few minutes extra, maybe. What's the time? It's time. Take a few minutes. I just want to write down the punchline, but before that, continue inductively. And you get a bunch of row n's, and you let rho be the inverse limit of the row n's. So that's the lifts to GL2ZP. And by Skinner-Wiles, this is modular. I won't write all this down because I said it orally. It turns out the deformation condition at P is the ordinary one. So, okay, so to finally, what's the punchline to why is the Selmer group big? I already said it heuristically, but just to do a little estimate, last board. Now that we have our rho, we do the same thing. We take psi, was defined over there. We twist rho by psi. We look at t and t prime. That's t prime is the isosceles, a prime is v mod t. So this dimension, we already had said, was greater than n by 2. The sum of all the Tamaganos and x, but there may be now many, many terms here, and this number might be going to minus infinity while this number is going to infinity. So this is a problem, but as I said, these numbers are 0 if delta L of A prime, if L prime, okay, 0 for type 2, for L of type 2 and type 3. So that's okay. So you only have to worry about the type 1 primes, which were coming up here, and I think right at the beginning. So what are you left with? N over 2. I'll write it here. So this is just minus what primes survive here. They're just the original primes x naught and these qi's. All the intermediate primes didn't matter here. Because these are 0. And now this is just depending purely on rho bar. So how many primes are here? Remember the delta L's were bounded by 2 when L was not equal to P and bounded by 6 when L was equal to P. So separating out those terms, these are the primes not equal to P. And there's also 6 for the prime delta P. And finally, there are the primes for the QIs, which are not L. Trivial primes according to 1 mod L, so there's a 2m here. Anyway, the point is that this whole number here is bounded. And this number can be made arbitrarily large. So you get that the Selmer P rank is greater than or equal to n for any particular n. Okay, and then to prove the main theorem, you have to choose the character beta carefully, but that's just some algebraic number theory.
Any questions?
Does this contribute to this well-known problem about rank of elliptic curve?
I have to see how this fits in the literature. Yeah, that's a very good question. I don't even know how Selmer of A is related to Selmer of T is related to Selmer of V and things like that. But I think the one thing is true is that this particular Selmer group, Bloch-Kato Selmer group, is the usual Selmer group in Silverman. That is true. So this is, yeah, even conjecture.
No, there are two types of variety whose rank goes to infinity. What does it know? No, no, but GL2 abelian variety gives you more room to play. This is just a dimension of it.
Yeah, it's a P part of the symbol, not the rank of the.
It is not the rank of the Selmer group of P. So that is too weak. It is, for all you know, it is all coming from star.
Yeah. Yes.
Star is mostly.
So actually what Matsuno proved was that the Shahs actually are large. He doesn't prove that
So,
the Selmer is large.
so
But
the
that's
set
a bit more
of
simple.
primes, which
Yeah.
are the trivial primes
Yes.
that you add the ramification,
Mhm.
it's a fixed set in which you, because at
Yes.
each step you pick some primes in trivial primes.
Yes.
So in a fixed finite set.
Yes, the set can grow depending on row bar, because sigma could be large, and you want to make L1 through LL large so that this term is large. But the point is you're choosing the primes cleverly so that the Tawa gamma numbers for those primes are 0. So this part is remaining bounded, and this part is tending to infinity. So it's the set of primes could be arbitrary, I mean very large depending on row, but the Selmer group is still large, P rank, because of this term.
But do they contribute to the ramification of rho?
Yes, they're in the ramification of rho, I guess. Yes.
And the
Yeah.
set is
Yes.
finite?
Yes.
It's a finite set.
Set is it's a finite set. Yeah, there are other results where you might have infinite ramification. It's not like that. It's
So
a
at each
finite
step, when you
ramification.
make the lift, you know
Yes.
something about the ramification of the lift?
Yes. So you can see up to this point, everything was finite, and this step is a recursive step. So once the set X at step 4, when you reach here, this set X remains constant. You don't add any more primes at this step. You repeat this step again and again.
Okay.
So this allows you to go to infinity.
Any more question? I have one question.
Yes.
I think in the definition of the Tamagawa number, you need to have a compatible system of Galois representation.
Okay.
So therefore, here it's very important that you have to use the Skinner-Wiles theorem.
Okay.
To do this.
Say it again. You need a compatible system of Galois representations to define.
The Tamagawa number is defined at each place for the corresponding Galois representation at that place.
Okay. So it's important to know that rho is modular?
So I think it's important to know that your lifting is actually modular.
Okay. You'll have to explain that one more time to me, but yeah, okay. It seems, yeah.
Yes, when you compute yes. No, otherwise the same condition at a given prime, the Bloch-Kato condition or the Greenberg condition will be the same. No, but well, we can talk about it there. So let's send the speaker again.
Oh, Somnath has a answer. You can go with that.